video sebelum ini sangat membantu.
Ya. Saya rekod. Cuma yalah rugi yang first lecture tu tak sempat tak rekod tapi ada masalah dengan sound setting, so tak ada sound, tak ada bunyi. So hari ni saya harap okey lah, dah test.
Doktor, rakan saya Wong Si Hui memang dah ada kat dalam ni.
Wong
Dia dah ada.
Wong
Wong
Sing
Si
Hui
Hui.
dia. Oh, okey. Wong Sing Hui tak ada. Sorry.
Asma dia tinggal.
Oh, okey. Wong Kam Irfan Asma, seorang lagi lah Asma. Asma under Dr. Chua kan?
Ya, Chess. Tapi dia tak cakap hari ni dia akan accept.
Oh.
Namun kita terus je lah. Nanti dia boleh lihat recording lah.
Okey. So maybe kita start. Mungkin dia ada masalah. Okay, so good morning again, everyone. So we will continue what we have done last week kan, writing Testbench, which is a very interesting topic in digital design. So last week we have learned how to write the Testbench for combinational circuit, and today we will continue with the sequential circuit. Alright, especially the finite state machine, that is very important in designing or building the complex digital system. So hopefully you are getting familiar with the Testbench from what we have learned last week. Yeah, from the example, from the discussion. So and from the tutorial, I hope that you have practiced writing the Testbench already. So for today, we will start with the finite state machine, because I think the theory of sequential circuit is actually have been introduced to you in digital design class and other VLSI courses, right? So let's look or go back a little bit. What is sequential circuit or finite state machine? And I hope that you have your quarters ready, because we will in this training we will use quarters, hands-on. I will share the file, the design, the example that we will use today in Telegram, so you can straight away use that design. So first, today we will look at, can you see the screen?
Yes.
First is, of course, the finite state machine, FSM. So FSM is one of the sequential circuit. What is the sequential circuit? The sequential circuit is the circuit that has a clock. Use clock to synchronize the data or the operation, and also the circuit that the output is not only depend on the present input, but also depend on the past behavior or the memory of the circuit. So this is very important in designing a complex digital circuit, where sometimes we need the circuit that behave in some way depend on the specification that we have. So for example, when we design or we want to design a vending machine to dispense candy, for example, or water, right? So for example, when we insert 10 cents into the machine, and the circuit or the controller or the system that we have must remember that the first input is 10 cents, so that the next input, for example, if we insert the next one 10 cents, so what is the action that we need to do? Or if we insert 20 cents, what is the action that we need to do? Or next, if we insert 50 cents, what is the action that we need to do? So in order to do this, the system or the circuit need to be able to remember what is the past output, or the condition of the circuit. So this require the sequential circuit or the finite state machine. So let's I think the detailed theory you have learned already. So we just do the revision. So we go straight away to the example. So I have the example here. Let me open this. Okay, so this is the example of a simple state diagram that represent the behavior of the finite state machine. So this is not the circuit, but it's a conceptual view of the behavior of how the circuit will behave. We call it a state diagram. And the number of state, this is state, right? And the numbers of state is finite. That is why we call finite state machine. So let's, for example, we want to design the vending machine that will dispense or for the candy, or will dispense the candy, and the price of the candy is 30 cents, for example, and this vending machine can only accept 10 cents and 20 cent coin, right? and it will dispense the candy, give the output when the total coins that we put in is 30 cents, right? So this state, and f equal to 1 means that dispense, the machine need to dispense the candy, right? And for example, we give more coins, for example 40 cents, means that we need to return the balance to the user, to the customer. So this is another state where, yes, of course, we dispense the candy, f equal to 1, and g equal to 1 means that we return the balance. So this is state number 4, 40. We call it 40. And this is state number 0, where when we start power on the machine, so our machine will be in this state. All right, we'll be always in this state when there is no input. All right, or we reset, or we power on. And when we insert 10 cents, it will go to this state. We call it state name 10. All right, and the output for this is f equal to 0, g equal to 0. And in this state, when we insert another 10 cents, so it will go to the state 20, and we insert 10 cents, it will go to state 30, dispense, and it will automatically go back to state 0 to wait for another input. All right. Or if we at this state, and the first coin that we put in is 20, so it will go straight away go to this state, and we put 1 0 or 10 cent, it will dispense, go to this 30 and dispense and go back. Or maybe we put 20 cent and another one is 20 cent, so it will go to this state and go back. All right, so this is the possible state diagram for the or to represent the behavior of the state machine that we want to design. Right. So again, this is the behavior. So now let's okay, so this is the behavior. Now what about the circuit? All right, so how can we design the circuit for this? So there are two type of finite state machine. The first one is Moore type machine, and the second one is the Mealy finite state machine. All right. So this one is Moore or Mealy? Anyone have answer?
Not sure.
Okay, the answer is not sure. Alright, so this is Moore type machine, Moore finite state machine. Yeah, because the output is in the state. All right, so this will be the Moore finite state machine. If the output is at the transition, for example, the output is here, or here, or here, that is Mealy state machine. So that is the difference between the two. So this is Moore. Yeah. So now, how do we have the circuit for this? So the circuit for finite state machine is actually quite straightforward. Yeah, we have the what we call the general form of the finite state machine, where first thing that we need to have is the state register or the flip-flops. Yeah. So this we call the state register. And again, we have learned how to design the register, right? This is actually flip-flops that we connect in cascade. All right, we have many flip-flops, so it become the register. So this one must be connected to another circuit, and this must be the combinational circuit, and we call it the output logic. And we have another one. This one is called the next state logic. All right, this is a combinational circuit as well. And we will have something like this. And this is a D flip-flop. Right, we can have the output here. So the output can be 1 bit, can be many bits, depend on the specification. And also here, the size of the register, whether it is 1 bit or 2 bit or 3 bit, is depend on how many states that we have. So in this case, how many state that we have? 1, 2, 3, 4, 5. 5 state. So to represent 5 state, so we need how many flip-flops? Right? To represent means that we need to represent or model this in digital format, because in digital, in circuit, we cannot have 0, 10, 20, 30, 40, the name like this, or A, B, C, D. No. All right. So what we need to have is that state 0, we need to represent with a number. All right. In our case, is the binary number. State 1 or state 10 in this case need to represent in number also. So if we use 1 bit to represent this, so if we have 1 bit, so the number that we can use is only 0 and 1, right? So in this case, we cannot represent all the state, because this can only have 2 numbers. So it can only represent 2 state. So we cannot use 1 bit. What if we use 2 bit? If we use 2 bit, so we can only have 0, 0, 0, 1, 1, 0, and 1, 1. So we can have up to 4 numbers. But we have 5 now. So we cannot use 2 bit. Now we use 3. So if we use 3, so we have 0, 0, 0, 0, 0, 1 until we have 1, 1, 1. So we have 8 combination. Now if we have 8 combination, of course we can represent all the state, because we have only 5 state. So in this case, we must use at least 3 bits. Means that we use 3 flip-flops. And for more type or melee type, we need to have a feedback from here to here. And we may have the input to the next state logic, or sometimes we don't have, depend on the specification also. All right. If our circuit, this is FSM, this is more FSM. All right. What is the difference in terms of circuit? Yeah, more and milli. So the difference is that for milli, you have another connection to here. All right. The input here also drive the output logic. That is milli type FSM. But for more FSM, you don't have this. So this is more. All right. So this is the general form of the finite state machine. And in our case, yeah, if we want to represent this one should be 3-bit. This one, the input, what is the input now? The input is the coin. Yeah. So we need to have the sensor that detect the coin, whether it is 10 cent or 20 cent. So let's, for example, because here we have how many possibilities? We have no input. Yeah, no input means that maybe 0 to represent no input. 1 to represent 10 cent. 2 to represent 20 cent. All right. So of course in binary, this one is 0, 0. This one is 0, 1. This one is 1, 0. So it should be enough. So in our case, the input here must be 2-bit. Yeah. And let's name this as W, which represent the amount of money or coin that we insert into the machine. Yeah? So if 0, 0 means that no input. If 0, 1 means that 1 cent. 1, 0, 20 cent. So we have 20 cent only, right? No 50 cent in our case. Okay, so that is done. So this signal is called, is the state, represent the state of our finite state machine. All right, this signal. So if the output of the flip-flop is 0, 0, 0, means that we are in state 0. If the output of flip-flop is 0, 0, 1, means that we are in this state. If 0, 1, 0, we are in this state, and so on. And the output here, because we have how many output? We have 2 output, F and G. So we will have 2 output, F, G. All right. So for example, in state 0, 1, 0, or in our case, this is 0, 1, 0, represent this, the output must be 0 and 0. And if we have here, yeah, the state where this output of this signal is, if this is 0, 1, 2, 3, so it should be 0, 1, 1 here. So the output here must be this 1, 0. Right? So that is how this is used to realize this behavior. Okay, so in digital design, actually you have learned how to design or how to derive the logic inside here, how to derive the logic inside here, and also you have learned how to write the Rtl code, yeah, to derive the logic inside here. So we will not go into detail in this, how to design the circuit here and here. We will jump to the Verilog code. All right. So I have the Verilog code for this, and I will share with you so that you can straight away use in Quartus. So let's I will share with you in Telegram. The design and also the Testbench, and we will discuss how to write the Testbench and how the Verilog code for that represent this circuit works. All right, before we go to the Verilog, any question?
No, Doctor.
No question, Doctor.
I think Asma is requesting to join. Okay. Asma? Dah masuk. You lambat. Asma, are you here? No? Okay, so please check. Oh, we have two person that not in a group kan. So I will share in the at the micro e WhatsApp, yeah. So you can get the file from here. Hold on. Wong and Alif, do you have Quartus installed with you?
Yes, Doctor.
Okay, good. So Alif, if you don't have, maybe you can refer to the video later. All right.
Okay, Doctor.
So I will share with the file. Okay, you get the file? Have you get the file?
Yes, Doctor.
Yes.
Okay, so you can open the project in Quartus and try to look at this. We will discuss. Okay, if you open the file in Quartus, so this is the Rtl code to represent this. All right, are you ready with your Verilog code?
Yes, doctor.
Yep. So now, in our case, this is the circuit that we want to describe in Verilog, and this circuit will behave exactly according to this. We have the output, we have the input in name W, and we have the register, and of course this register you need to have clock, and also the reset signal, right? So that is why we have this clock reset, and this is W, the input, the output F and G, and this is just for reference. In this case means that I have the connection here, connect to the output called state, so that I can observe the state, yeah, in the simulation later on. So this is just for simulation purpose. Yeah, I want to see, for example, in at state 1 what happened, at state 2 what happened, and so on, right? So that I have this. The input, of course, clock and W, and also we have clock reset is 1 bit input, yeah, clock and reset, and we have W 2 bit, we have W1 and W0, and we have output F and G, and we have this one state output also, right? And both here must be declared as rack data type as well, because we will use behavioral modeling. Yeah, we will code in behavioral code. All right, so for your information, normally, yeah, for the finite state machine sequential design, we will code using behavioral code. All right, sometimes people refer to this as RTL code. Yeah, so is actually RTL is more detailed than this. We will maybe I will touch a little bit on RTL later on. So we have these two signal. This one we call, of course, we call the state, and we have another signal. Here is the signal. This signal is called next state signal. All right. So this is next state. So this is 3 bit. Yeah, 3 bit. 2 to 0, 2, 1, and 0. 3 bit. This one is 3 bit. And we have the state name we declare with parameter. So it is 3 bit 0, yeah, or in binary is 0, 0, 0 to represent this, and we have 10 to represent this, which is 0, 0, 1. 20 is 0, 1, 0, this one. 30 is this one. 40 is this one. All right, and now we want to describe this, the state register. All right, so to model the flip-flops or register in Verilog is actually pretty straightforward, pretty easy. So this is the code to represent this, where we have the always block, positive edge or post edge clock, means that this register is positive triggered flip-flops, and post edge reset means that the reset is active high, and when we write like this means that this reset is asynchronous. What is asynchronous? Asynchronous means that it is not reset at the edge, but reset refer to the level, means that whenever the signal is 1, the circuit or the flip-flop will reset. Right? So the code, if reset equal to 1, so the output here, the name is state. So this is state. The output will be equal to 0, and this case is means that 0, 0, 0. All right, means that when reset, we are at state 0. But if not reset, or the reset is not active, so the output here is this, because this is the flip-flop. So the output will be this next state. State will be equal to next state. Right? So this is this will create or will be synthesized into this. Now we want to create these two logic blocks. All right, so you can create separately, or you can combine these two, because both are combinational circuit, and this is actually connected, right? So in this case, I combine these two. So I name this part as next state and output logics. So to do that, because the output here for this one, the output logic, will depend on this, this input will depend on state. This one, the output for this logic block is this one. This is the output. The next state is the output for this, and the input for this is this. From here also the state, and also the input from the outside, the coin. So to code in behavioral, we use the always block. So all the input that we have is, yes, of course, the W, and the state, this one. All right, and because we have many possible outputs, so the best way is to use case statement. All right, you can use if else, but the easiest way is to use case. Case state here, we refer to this because we have many states. If we are here, what we want to do. If we are here, what we want to do. What is the next action that we want to do? What is the output? And where to go next, right? So we could use case state. So for example, if state equal to 0, 0, 0, or we are in state 0, so what we want to do? First thing, if we are at state 0, of course, the output is F equal to 0 and G equal to 0. All right. And now output is easy, right? Now the output for this one is easy, F and G. So F equal to 0, G equal to 0. Now the output for this one. Next state, the output for this one. So the output for this one will depend on this W. So W, we have how many conditions? We have actually 4 conditions because this is 2-bit. So if 0, 0, if W equal to 0, 0, so what we do, the output here, the next state, the output here should be 0, 0, 0, means that if we are in state 0, if we are in state 0, if there is no input, so we should stay here, right? We should stay here, means that the next state must be 0, 0, 0 also. So that's why we have this. But if the input, if the input is this 10 cent, means that 0, 1. Remember, is 0, 1 represent 10 cent. If the input is 10 cent, so the next state must be this 0, 0, 1 here. This state is represented by 0, 0, 1 or 1 in this case. If 1, 0 means that 20 cent, so the next state must be this one, 20. So must be 0, 1, 0, 0, 1, 0. Yeah, 20. If 20 cent, the next state is 20. We have another one possibilities, yeah. Although this is will not happen because we not represent any other inputs. We have only 2 coins, yeah, 0, 1, 10 cent and 20 cent. But in Verilog, we need to have all the possible conditions. All right. So in this case, if the input or W is 1, 1, so we should stay at this state also. Right? Nothing happened. Right? For example, you put 50 cent. All right. So because our machine not receive that, so we stay here. All right. So this is the state 0. What about this state? So this state, again, the output easy. Both are 0, F equal to 0, G equal to 0. And we look at W. If W equal to 0, 0 means that there is no input, so we wait. So we stay in state 10. If 0, 1, means that 10 cent is inserted, so we go to state 20. If 20 cent, so we will go to 30. But if other than that, we should stay here, right? Or maybe in your state diagram, you have another state to reject. For example, if you insert 50 cent, you have another state that it will reject that coin, right? But in this example, we don't have, so we stay 20. So this is the code, and 30 is easy, right? Look at 30. When we are at 30, so the output is F equal to 1, G equal to 0. And at 30, we will not look at the input anymore. All right, we will ignore W. All right. And here, straight away, we will go back to state 0 because 30 cent already, so we need to dispense. All right, no need to wait for another input, so we'll go back. 40, also the same. When 40, F equal to 1 means that we dispense, and G equal to 1 means that we need to return the balance, and straight away we go back. All right, and again, yeah, because state here is 3-bit, so 3 bits means that there must be 8 possibilities for state. Yes, 0, 0, 0 to 1, 1, 1. But we don't represent all the state. We don't have up to 8 state. So you need to have this. Yeah, means that other than that, F should be equal to 0, G should be equal to 0, and state should be at state 0. This is very important. All right, or this is called the synthesizable code. Yeah. So remember, when you code in Verilog or VHDL, you should know exactly what will be your code. What will your code be synthesized to? All right. So if you don't have this, when you compile your design, you will have many warnings. Yeah. Because the Verilog will automatically assign the value for you. And the warning sometimes is okay, sometimes it's not okay, depend on what is your specification. All right. So make sure you don't have any warning and of course error when you compile, right? So in this case, other than this value, so we set the value of this is this. Because remember, this is not computer program. This is the code that is used to synthesize or to create the circuit. So the circuit at any time, the output must have value. All right. So in this case, if you don't have this, means that at certain part, your output don't have value. This is wrong, right? In hardware. Okay. Now, after that, you can close your case statement here to close this case statement, and you can end your module here, right? So this will represent this, and it will create this circuit, right? Now you can actually compile. In our case, we don't compile because we not implement this in the actual hardware yet, right? And also we will not look at the timing yet. All right, we want to see whether it's work or not. Yeah. So we use analysis and synthesis. Yeah, means that it will check for any syntax error and try to create the netlist, create the circuit for you from this code. So if you have your code now, let's start analysis and synthesis together and see whether we can have correct output or not. All right, and this is important. Okay, looks like slow because I have many software open. My memory is quite full, maybe. Okay. All right, done. So no error and one warning, and this warning is okay. This is not regarding to the design, but this is because the license of the software where we use the light edition or the free version. Hold on, let me try to close some program. Okay, do you have any error or more warnings?
No.
Okay, so because this is the exactly the same as this one, so it should be no problem. So now we want to test or to simulate our design. So we will use the Testbench, right? So the Testbench is also given, so you can straight away open your Testbench. So you can open your Testbench. The name is this. All right, so this is the Testbench written by me. So quite long, and I will explain here. We have a little bit different from what we have last week, where now our circuit have clock, and the good thing is that we can refer the time to the clock in this case using this. Yeah, at negative H clock, what we want to do. At positive H clock, what we want to do. All right. So again, the attachment, you need to have the time scale, your module, and your input output for your attachment. You need to instantiate your design. So this is how you instantiate your design. The name is wending 2 in this case. So you do instantiate, and we name it as design under test, and we use the positional port map here. Make sure that the position of all of this must be the same as this. And this is how you create the clock in Testbench. All right. So there are two methods. I give you the first one here. You can use always. This is time, means that every 10 nanosecond. Why 10 nanosecond? Because our time scale is 1 nanosecond. All right. So if I write anything here, time here, 10 means that this is multiplied by 1 nanosecond. If I write 10 nanosecond, means that the time is 10 multiplied by 10 nanosecond, which is 100 nanosecond, right? But in this case, it means that every 10 nanosecond, we what to say? We toggle the clock. Yeah, clock equal to not clock. This one, and remember, at time 0, we need to in the initial block at time 0, we need to set the clock start at 0 or 1, depend. All right, in this case I use 0. So if we write like this, what happens is that we create the clock like this. At time 0, so the clock will be 0. Yeah, logic 0. This is logic 1, for example, logic 0. And it will 0 for 10 nanosecond, and will go to 1 here, and it will be 1 for 10 another 10 nanosecond, go back again to 0, another 10 nanosecond, and go again. All right, means that the period is 20 nanosecond. Right, so in Verilog, if you write like this, means that your clock is toggle every 10 time unit. In this case, 10 nanosecond. All right. Another method of creating the clock is this, where we create in the initial block. All right. So you use forever keyword, forever. All right, so here you should have time 0, clock equal to 0. Then you can create the clock here. And of course, when you have the initial block, you need to have N here. So this is another way to create the clock, yeah, with 20 nanosecond period. Right, so you have two options, whether you want to use this or this one. Both are creating the same clock signal. All right, when you write, but if you have this, yeah, clock equal to 1, you start with 1, means that your clock will be like this. Instead of starting from at time 0 here, it will start with 1 for 10 nanosecond and go back to 0 at 10 nanosecond. So your clock will be like this, right? So we start with 0. So if you have this, so here no need to have this. So your clock is created here already. Okay, now let's look at this. So this is the stimulus that we want to create, all right, to see whether our design is correct or not. All right, so this need an experience and creativity, yeah, how you want to test your design. So in this case, let's look at this. So this line means that at time 0, yeah, if this is the clock, and remember we create the clock already, and our clock will always run endlessly. Okay, and then this is 20 nano. This is 20 nano, this is 40 nano, 60, 80, 100, 120, and so on. All right. Now, here we have a reset signal and W. So let's say, for example, this is reset. Okay, so at time 0, reset equal to 1. So time 0, the reset, this is 0, 1 also, equal to 1. So we start here at time 0, yeah. And W, we also have W, and W is 2-bit. So 2-bit, we represent with data, yeah, the timing diagram is represented as something like this, yeah. If data is 0, 1, 1, 0, and so on, right? So in this case, again, at this is 0, at 0, so we start with W equal to 0, right? So that's it for this line. What about this? This line means that another 25 nanosecond, something here, because this is 30, right? This is 30, so 25 should be here. Should be here. At 25, what we do is that we force the reset signal to be 0. So before that, it should be 1 until 25 nano. It go to 0. That's it. And what about W? W is still 0 because we don't change anything. So it will remain the same. So it should be always 0 here until here, 25. Now, this one. This is a good thing about writing the Testbench for Verilog, where we can refer our signal to the clock signal. All right. So at 25 nanosecond also, and the next negative edge clock means that where is the negative edge? So this one, yes, but we are now here 25. So this is past already. So the next negative clock edge will be this one. Yeah, this one. This one, not this one. Means that we refer to this one. Clock edge, and at another 5 nanosecond. Why 5 nanosecond? So this is depend whether you want to 5 or 2, because normally after this, or we don't want to check any output at exactly at the same, or not the same, at the clock edge. Yeah, because the output is not stable yet. So we will check the output a little bit after, shortly after the clock edge. So in this case, we delay a little bit, 5, this, not this one, yeah, this one. So here we change the input, no problem. At this one, we also change the input, W equal to 1. So we have W equal to 1 at 25 also. Oh, sorry, not 25. At the clock edge. Yeah, negative clock edge. This one means that we have W equal to 1 here. And we want to display this. Yeah, insert 10 cent in the output window. Later on we will see, right? When we input 10 cent at another 5 nanosecond here, means that 45, right? At the 45 here, we want to display insert 10 cent, right? Just to display to the window this. And we want to check this one, we want to check the output. All right, whether we are, if is W equal to 1, yes, of course, W equal to 1 means that this is the input, right? If W equal to 1 means that we insert 10 cent here at 40, at 40 nanosecond, we insert 10 cent. Why 40 nanosecond? Because of this. We insert 10 cent. And we display, yes, we insert 10 cent. And now when we insert 10 cent, we want to see the output of our design, whether it is correct or not. So based on the behavior here, when we are here, when we insert 10 cent, we should be in this state. And when we are in this state, the output F and G should be both equal to 0, 0, and we should be in this state. How to know that we are in this state? We check this signal, the state. So the state must be equal to 0, 0, 1, right? This 10, 0, 0, 1. Okay. So it must be 0, 0, 1. So let's check here. So this is how we check. So where to check? So the safe place to check, right? Because we insert here W equal to 1 here, so it will be always 1. So the best way to check, so the state, yeah, the state signal, let's say the state signal is here. So it should be always 0 until here. So according to our timing diagram here, and because this is positive edge, so when W equal to 1 here, it must be go to state 1 here, exactly at the positive edge here. So this is W should be equal to 0, 0, 1. No, not W, sorry, state should be 0, 0, 1. Right? This is the output that we expect. Now we want to check whether it is correct or not. So in our testbench, we can write something like this. If state equal to 0, 0, 1 or 1, right? 0, 0, 1 is 1. All right. So we display this. But if not equal to this, we display this incorrect. All right. And we display the state. Yeah, the state. And also the output. Okay. So when to check? So we check at this. After this, we go look at the post edge. So should be, yeah, after this, where we are here, we are at next edge plus 5 nano. Next edge plus 5 must be 45, and the next positive edge should be this one, positive edge, and we go another 5 nano to be safe, should be, so this is 50, should be 55 nanosecond, and we check. So this is the place that we check whether this is 0, 0, 1 or not. If 0, 0, 1, we display output correct. If not 0, 0, 1, other than that, we display incorrect. Right? So that is the first thing we want to check. Now let's see the output. The output when we run this testbench. So again, you need to do the setting, right? And make sure that you go to simulation. Here, select the model sim Altera. Select Verilog, and you create the testbench. This one I create already. So you give the name, and you must have the file here. You need to add the file, right? So in this case, this is done already. So I just go to RTL simulation, click, and we see the output later. Okay, this is the model sim window. Okay, we have the output, and this is the waveform. And let's look at the first that we have. So this is the all output that we have, yeah. So let's look at the first setting first. At the first, this, yeah, from here to here only, right? So at 45 nano, so this is the time. How to display this time? So in the Testbench, you just have this, yeah, display time, yeah, display time, and you will get the time, yeah. So 45 nano, exactly 45 here, yeah. 45, we say that we check, or not check, we display insert 10 cent, okay, exactly here. We want to display this at the 45 nanosecond, all right. 25, after 25 nanosecond, the next clock edge, yeah, remember, after 25, the next negative edge, which is this one, and then plus 5 here, 5 nanosecond, which is 45. So at 45, here we display insert 10 cent. So that's why we have this display insert 10 cent. And at 55, exactly here, yeah, 55, we are in state 1, and the output is F equal to 0, G equal to 0. So the output is correct in this case, in state 1, 55, right? Why we get this? Because in our Testbench we write, yeah, if state equal to 1 or 0, 0, 1, we display this. That's why we have this in state, right? So state now correct, because our design is correct. So the value in state is 0, 0, 1. So that's why it shows 1 here. And we display in decimal, all right? So if you change this to B, it will display here 0, 0, 1. Yeah, in our case, it's D. And we display F, we display G, and because this condition is true, so that's why we have output correct. But if the condition is not true, means that because our design is wrong, so it will display this incorrect, right? So correct. So let's look at the others, this, yeah. So I will not go to all of this, so you go back and study, right, this. And let's look at the output, the simulation output. So when you insert 10 cent, yes, you go to state 1, the output correct. So this will exactly refer to this. In state 1, F equal to 0, G equal to 0, so correct. And when you insert 20 cent, you should go to state 3, right? When you here, insert 20 cent here. So you go to state 3 here, 30, this one, state 3. And of course, when you are in state 3, here, F equal to 1, G equal to 0, right? Means that this is correct. And it will, the next clock cycle, it will go back to state 0, and this is correct. So if you insert 10 cent and 20 cent, this what will happen, and this flow is correct. Then checks another flow. For example, you insert 10 cent, so you will go to state 1, Insert another 10 cent, you will go to state 2. Insert another 10 cent, you will go to state 3, and it will dispense the candy. Go to state 3, and this is correct also, back to state 0. And now you check another flow. Insert 20 cent, so it will go to state 2 here, and the output is correct. You insert another 20 cent, it will go to state 4, and this is the output. Go to state 4, and the output is correct. So all are correct. So if you have any incorrect here, you need to go back and check. So this is the timing diagram where we can see the time here. For example, this is exactly what we have here. All right, the clock. So this one is 25. So here we have 25, and W equal to 1 at 40. So look at this, where is 40? This is W, and this is 40. So we change to 1 exactly, and the state will change at the positive clock edge here, because W changed to 1 here. The first positive clock edge, the state will change to state here, to state 1 here at 50, about 50 nanosecond, exactly what we have, 50 nanosecond here, go to state 001, right, and so on. And in this case, W will only active for 1 clock cycle, yeah, because it depends on the sensor. So we need to understand this also, where after we insert, so it will go back to 0, right, because it will not for a long time, right, 0, and wait for the another input. So for example, this one, we insert 01, go back to 0, insert again 20 cent, and the output here, F equal to 1, and this pen we go back to state 0, right. So this is actually state 3, state 0, state 1, state 3, right. And because in our code, yeah, Rtl code, we have this state at the output. That is why we can see the state here, right. That is why I have this in our code as well. All right, so this should be brief. All right, should be a revision for your digital design class, and I hope that this briefing will refresh your memory, yeah, about the finite state machine and how to design using Rtl HDL. Maybe the new thing is that the Testbench writing, yeah. So in this intern, so we will learn more advanced Testbench technique, where this is actually new for you, yeah, was not introduced to you before. Okay, so I hope that you practice this so that we can do a project starting this week, right? Okay, any question? Remember, this is meeting, so we should have two-way communication.
Doctor, can you please explain again about the output state, the condition? I want to more clearly.
Okay.
Don't
Means that
understand.
uh,
Repeat.
means that your detachment, right? Yeah.
Yes.
Okay. In this condition, yeah. Yeah. Right. Is it?
Yes, doctor. Yes.
Okay. Okay. So let's look at this again. And again, the testbench is up to you how you want to write, how you want to test your design. To know, the objective is to know whether our design is correct or not, and behave exactly what we want our circuit to behave, right? So we need to keep in mind that our circuit should behave exactly like this. So we need to design our testbench also, so such that we can see when we have this input, our circuit must produce this output. All right. For example, if we are in state 0, if the input is this, what next? Where we want to go, and the next state, and what is the output? That is the objective. So in this case, see, this is my testbench design. So in your case, maybe you want to do different way. So it's actually up to you. There is no, there is no correct. Cannot say that my one is more correct than you. All right. So as long as your testbench can produce or can give you or shows that your design is correct, to the testbench prove your design correct, then this is okay. So in this case, this is my testbench design. So I want to see if I start here, I put 1 cent, what happened? Okay, so we need to think in the time line. All right, in the timeline. Remember, we are electronic engineer. We need to be able to interpret the waveform, the time. Time at this time, what happened? At this time, what happened? So here, I start with this, where time 0, I reset my circuit. All right, this is how to reset, right? Why reset equal to 1 is reset? Because according to this, our reset is active high. Means that if it is 1, we reset. Okay, so we reset. And also, there is no input yet. Means that W equals to 0 at time 0. So, oops, sorry. Okay, so so at time 0, and again our clock start at 0 at time 0, so reset equal to 1, W equal to 0, exactly here. And now for 25 nanosecond, at the next 25 nanosecond, I want to deactivate my reset. Right, means that I force the reset signal to 0. So exactly at 25 nanosecond, it will go to 0. So this depends. You want to deactivate at 20 or 30 or 35, depend on you. But in my case, 25 nanosecond, I want to deactivate my reset. Means that I will, because when reset, I will be at state 0. And it will be in state 0 forever, except that you have this input or this input. Other than that, you will be always at state 0. So at state 0, we want to simulate. If we have 10 cents, what happened? If you have 20 cents, what happened? All right, in this case, I give 10 cents. Okay, so give 10 cents. So it depends also whether you want to use the previous technique that I explained to you last week. All right, using the timeline where maybe at 30 nanosecond you want to check, or give W equal to 1. But this one is a little bit difficult because you need to keep track the time here. All right, and remember it is accumulated. The best way is to refer to the clock, relative to the clock. So this is a good thing where we can use the clock as our reference. All right, so for example at 25 nanosecond, and we look at the next negative edge of the clock. So this is the how to write in Verilog. All right, at 25, the next negative edge means that we are here now. Where is the next negative edge? Here, right? Not this one, because this one is the second one. The first negative edge after 25 nano, which is this one, not this one, because this is 20. Remember, we must we need to imagine, we need to look at the timeline. We are at 25. The next negative edge, we want to do something. So this should be at 40 nanosecond, and we want to force W equal to 1, means that we insert 10 cents, right? Exactly here. Insert 10 cents. And at another 5 nanosecond, 5 nanosecond here means that after this negative edge, 5 nanosecond, which is 45, we display insert 10 cents, right? We not check the output yet, but we just display that, okay, here we insert 10 cents. Now we want to check. So when we insert 10 cents here, 10 cents here, so at the next positive edge, we should go to this state, right? Because our here is positive triggered. So it will change to the next state at the next positive edge when the input change. So when the input change here, it will not immediately change to the next state here, but it will change to the next state here at the first positive edge after the input change. So the input change here. So see, we should go to the state 1 if we insert 10 cents. Now, just like I said last week, when we want to check the output, we know that the output will change at this, right? But don't check the output at the exactly the same time as the input change, because the output will change a little bit later because we have signal delay. So we need to check later. So later how much? Depend on your design also. So to be safe in this case, I check after 5-second delay. Means that somewhere here or 55 nanosecond, I check the output whether it is 001 or not. In this case, the state, right? If 001 means that our design is correct, at least until here, at least when we insert 10 cents if we are in state 0. All right, so here we can check after the positive edge clock. So let's go back here. where we are here. We are at negative h plus 5, 25 negative h, remember, should be here, right? 45. And post h clock must refer to this one, right? Because the first positive h clock should be this one. And then after 5 nanosecond should be at 55 nanosecond, I test. This is the condition. So you asked here, right? So if state equal to 1, so I check if state equal to 1 or 0, 0, 1, so the design must be correct, at least until now, until here. All right, so if state equal to 1, so we just display this. And if you want to see the time, so you can have this one, or if you don't want to see the time, so you just remove this one, no problem. All right, but for verification purpose, better to have this. So you have time, and this one just like in C++, yeah, or C when you want to print F. All right, so this one it means print what you say here, and this one percent, when you put percent here, it will actually refer to the number. All right, so it will refer to what you have here. So the first one is %d in decimal, and you show the state. So this is automatically assigned by the software. So if state, yeah, the output, the state is equal to 0, 0, 1, it will show 0, 0, 1. If the state is 0, 1, 0, it will show 0, 1, 0, right? F, G, G, and this one is in binary, this one is in binary, and we show output correct. So if the condition is true, it will check state equal to 1 or not in this case. Equal to 1 or not. So if equal to 1, like this, it will display this. But if the state not equal to 1, means that here instead of 0, 0, 1, when you insert 1, you have, for example, 1, 0. Oh, sorry. 1, 0 here. You have 1, 0 here. So means that this condition is not true. If this condition is not true, it will display this. If display this, it will show time, the time, of course. State, it will show what? State. State, it will refer to this signal, which is 0, 1, 0. So it will display 0, 1, 0. What is the output? F at this time, B, G at this time. This should be %B, not 5B, right? %B. And it will show incorrect. Because in our case, the output is correct, that's why it shows this one. Because the condition is true. Here's the one. If it is not true, it will show instead, depend on the condition, the value of state in this time, whether 002, 003 or others. And it's, of course, it will show output incorrect. Because in our code, we say if it is 1, you show this correct. If other than that, must be incorrect. All right? Okay, Kam, is it clear?
Yes, doctor. Thank you.
Okay, ada question?
No, okay.
Okay. All right, so if no question, I think, yeah. So you can, because well, you have many more, yeah, for to test all of, I mean most of the possible condition. So it will show this. All right.
Okay, I hope that you can share the video later on.
Yeah,
If you-
Irfan, louder.
I hope that you can share the video that you record
Yeah,
just
yeah,
now.
yeah. It's recorded, and I hope the I think the I mean the output is okay. All right. So if you're okay on this, we will go to the project that we want to do for the remedying of the intern. Okay, or you want a break? 5 minutes?
I think just continue. For me lah. For me, just continue. I don't know.
Okay, just continue, yeah. Okay, so the project is actually based on what we have today. We will use the finite state machine to create the circuit. All right, and the project is actually is quite practical in terms of application. Yeah, it's look easy, but if we look in the details, there is many details that we need to consider. All right, so let's go to the project. Okay, this is actually the traffic light controller. This is a traffic light controller, which is a very practical project where we can have many type of traffic light controller and many technology that can implement the traffic light controller. So what we have in the market is actually using the PC, the computer, for the controller. So the disadvantage of using the PC is that it is big. All right. If you look at the controller, right? So let's a little bit see. Do you know where is the controller of the traffic light in at the traffic light? You know where is the controller located? So you can, if you observe, yeah. Let's look at our UTHM, right? This is the UTHM main entrance.
Rindunya UTHM.
Ya.
Lama tak balik UTHM.
Rindu UTHM. Hopefully, you can yang boleh tengok ni pakai Google. Where? Oh ni traffic light bukan kat sini . This is the main entrance kat sini. Okay. This is the traffic light entrance tu. Ni. So pergi sini sikit. You nampak ni? Nampak ni? Nampak?
Yes doktor, nampak.
Ni.
Nampak.
Nasib baik ada Google Map kan, boleh tengok. Kalau you rindu UTHM lah, you say lah ni UTHM ni stadium kan, ni library. Alright. So yes, everyone is missing UTHM kan. Ni ialah controller kat dalam ni. Dalam ni ada komputer We have computer inside here, the PC, the complete PC. So used to control the operation of this traffic light, and this is online connected to the main controller in KL. Depend on the traffic light provider lah. So normally they use PC as a controller. So of course you need to write a program to do the things. But in research, we can propose the other options. For example, we can use FPGA or even microcontroller. But microcontroller, of course, the performance and also the limitation lah, in terms of the number of I/O, the number of operation that you can perform. So normally microcontroller is not very suitable. For example, Arduino apa semua tu, alright, actually you cannot use to for traffic light controller lah in practice, in the real application. But using FPGA is very feasible because FPGA can create a very complicated circuit. Alright, even you can create a microprocessor using FPGA. So the good thing about FPGA is that the performance is good. Small, low cost, alright, and it is reconfigurable, means that you can change the design just like this. Alright, when you want to change the design, you change the code. Right, and it will change the configuration, the circuit in your FPGA. Okay, and the best thing is that it is small, right? So instead of you have the very big like this, maybe you can have a very small, all right, embedded somewhere, and very small circuit, right? So in this case, we will try to use FPGA as an alternative to conventional PC as the traffic light controller. So let's take a look at the example. All right, the T junction like this, just like the main junction, UTHM main junction, where we have T junction. All right, this is main road, and this is the junction to UTHM. Like this is UTHM, and this is main road. And let's look at the very simple sequence like this, not the real actual sequence yet. Remember, when you want to design something, don't start with complex design, you start with simple one. All right, so let's look at a very simple sequence like this first, where we have the flow like this. For example, when we have only three lights, three traffic lights, means that for this flow we call it L1. For this flow, we call it L2. For this flow, we call it L3. So the first flow, L1, is from, for example, from Kluang to Batu Pahat, and for U-turn and for entering UTHM. L2 is from the Batu Pahat to Kluang and to U-turn back to Batu Pahat. And of course, this one is always, go to UTHM is always green, right? And L3 is from UTHM to here, right, to Batu Pahat, for example. So that is the flow. So the normal sequence is quite complicated as compared to this, where you have, for example, this you have two light already for this flow L1, where this one red, this one still green, right? But this one we take use a simple one first, simple one first, all right? Of course, your project is more complicated. Where when L1 is allowed to go, all right, from here or go to here, so all other lights must be red, all right? L2 is red, L3 is red, right? So that here can go. But if L2 is green, the others L1 and L3 must red. If L3 green, L1 and L2 must be red, right? So that is very simple sequence. Okay, now how to create the circuit for that? So of course you need a timer or the counter to create a sequence. All right, so the sequence is that green how long, yellow how long, right, red how long. So of course red and green is should be the same timer, because if this one green, the others must be red, so you can use the same timer. All right, but yellow of course different. So maybe we can have a counter like this. Okay, so this is a counter. A counter is a register you can create using a finite state machine also. All right, or just a counter, a register. This is a register, and you have something like this, a multiplexer here. This one, the select input here we call T enable. This one we call T select. So T select means that we want to select the time. This one is 20. 20 means we count from 20, and this one, if you look here, this one is subtractor -1, means that if the value inside this is 20, you minus 1, so it will be 19, 18 and until 0, right? Count down. So if the counter count every 1 second, means that this should be 20 seconds. And this one is 3 seconds. We use for yellow, so yellow is 3 seconds, and 20 is for green, 20 seconds. All right, and this is 5-bit size. So this is the counter that we want to use. And when the counter is equal to 0, we have the output signal, we call it T out, and time out. So this timeout signal will be activated so that we can do something, right? So this is the counter, and this is the controller. All right, where if you look at this is actually the FSM, the state machine, finite state machine, and we have here is 4-bit. All right, we will see later why 4-bit. And the output is, we have L1. So this L1 is this, something like this. We have L1, and this is 3-bit. So if 100, if L100 means that this is actually this is green, and the red is on, and the yellow is off, and the red is off. Yeah, if 100 means that green on, this green, yellow, red, green on, off, off. So what about L2? So if L1 green, L2 should be red, right? L3 should be red also, means that red equal to 1, right? So that is means by this output. And T enable is this connected to this, so it will enable the counter to start to count. T select means that we select whether we want to for this. So if for green, we need to select this. If for yellow, we need to select this one. So this is the signal. And the timeout for this will trigger this controller, meaning that if timeout means that we need to do something, whether we will need to change the state from, for example, from this green need to go to next other state. Maybe now we have yellow, and the next still red, right? But this one yellow when the time is out. So this is the things. And the connection between the two is something like this. Yeah, it is this one, but we will change to the module view. It should be something like this. Now, the main problem, not main problem, the main issue, the challenging part is that how to create the state diagram to represent the behavior of our traffic light, right? The state diagram. So this is the state diagram, right? So to use this kind of state diagram is actually not very practical for the things that complicated as the traffic light, because you will have many more states, right? So the more practical way to create a state diagram is to use what we call the ASM, which is algorithmic state machine. So we will use algorithmic state machine chart, which is actually to create FSM also, right? But the behavior is not drawn like this, but we use the flowchart, right? This is called ASM, right? To represent the chart, the behavior. So you see this this rectangular box represent the state as 0, as 1, as 2, and so we have, for example, in this simple flow, so we need to have 12 state, yeah, as 0 to as 11, 12 states, and this is how, right, to represent better using this one instead of state diagram. So we use ASM. So the same ASM. So let's look at this. So this is the first cannot So this is the first state. So S0 means that when we reset, we will go to this state. So I name this state as L1 green, L1G is green, int initialization. And when this initialization means that all the lights are red, in red, L1, L2, L3 in red first, all right, in red. And this is only one clock cycle. And what we do here is that we set T select, whether we want to set timer to 20 seconds or 3 seconds. In this case, so we should set at 20 seconds, right? Because green should be 20 seconds. And we should select T enable. So this means if I write like this, means that T select equal to 1, T enable equal to 1. If equal to 0, T select equal to 0, I use this star like this, means that T select equal to 0. So why? Because to write this, it use more space, right? So the easiest way is this. That means that T select equal to 1. So what happens if we do this? Means that T select equal to 1. So of course here we'll go to here 20. T enables equal to 1. Remember, T enabled equal to 1 means that 20 will go to here. Means that 20 is in the counter. 20. And then next clock cycle. All right. So if our clock is 1 second, yeah. So it will go to the next state. I name it L1 green, L1G on. L1G green on means that this state L1 is green, 100 green, and of course L2 and 3 are red. All right. And I wait for T out is activated to go to the next state. So if T out is still 0 or not activated, so I stay here. So if remember, T out is generated by the counter, this counter. So it will count from 20 minus 1, 19. So if it is count every 1 second, so it required 20 nanosecond here. All right. So when T out equal to 1 activated, so I go to the next state. Not here, sorry. Here. Next state, which is L1 yellow. All right, because after green must be yellow, right? So we want to initialize the yellow. So of course we can start yellow already. So this is yellow, 0, 1, 0 means that yellow, and others still red, right? Others still red. Yellow. And now let's see, T select equal to 0 now, T enable. So let's go back again here. T select equal to 0 means that 3 will go to here and we enable. 3 go to here. Means that here we'll go to here and stay here for 3 seconds only. 3 clock cycle. 3 cycle. Alright, so it will yellow for 1, 2, 3. 3 seconds and go out. Go out. Now we initialize the L2 green on already. But remember, in practice, yeah, if actually not from yellow, it's not changed directly to red here to green immediately. It will need 1 second or 2 for safety reason that all the light is red first, right, before L2 turn to green. And the sequence is repeated actually. This is the same. We load 20 the timing 20 seconds into the counter here at the initialization, and then stay here for 20 seconds, green, and then yellow, and then now green for L3 and yellow for L3, and go back, green for L1, right? So this is the ASM chart for a simple sequence like this. Now look at the Verilog. All right, so I will share the Verilog code as well. Maybe after this, yeah, so that you can study. Okay, let's look at the Verilog code for this. All right, so I have 3 module because I have this module. The name is counter module. This is the controller module, and I connect both all of this to be the traffic light controller, the complete module. This is the top module here. So in this top module, I have the counter and traffic light controller. All right, so if we look at the counter, so this is a counter. So you go back and see how I create the counter to have something like this. Yeah, for this. And the next one is, of course, the controller, the most important one. Where is it? The controller. So this is the controller, exactly based on this ASM chart. So let's see. Okay, so we have the controller and all the state here. The name is exactly based on this. So remember, when you design the digital system, ASM, so the name is very important. So please name it accordingly so that you can refer it directly to this. So for example, L1G INT is this one, L1G ON is this one, and so on. All right, so this is state 0, this is state 1, and so on. So we have how many states? We have up to state 11. In total is 12 states. And this is the state register, very easy, same as what we have previously, yeah, except that the state now is 4-bit because we have 12 states. So 12 states, we need 4-bit in order to represent all the states. So if we have 4-bit, we can represent up to 16 states. So 12 is okay. Now here, at state this, state 0, so T select equal to 1, T select equal to 1, T enable equal to 1, and the output is exactly based on this 001, 001, 001, right? And this is only one clock cycle, and we go to the L1G on next state. The next state here, L1G on, we have a test here, right? So the first one, this one is actually not activated, so we set at 0, 0. But remember, in Verilog, you need to have the value, right? The value. If not, you will get the warning, right? Yeah, the warning is not from me, but from the software, yeah, when you compile. So here, the output here is 100, 001, 001 exactly. And here, if T out equal to 1, means that activated, so the next state must be this one. But if T out is still 0, not activated, so we stay in this state. All right, so this exactly will make us remain at this state for, depend on what is inside our counter. So in this case, we have 20, so it should be 20 seconds before we go to this. And the rest, it should be the same. All right, you can copy and paste and change the value. All right, so this is good. The good thing about programming is that it's actually repeated. All right, so you can actually copy and paste and change the value. You see, the structure is the same. You change the value. Right. Now this is the controller, and you have all the things already, and you combine both. You instantiate the controller module and the counter module and the controller module in one module, and you have the design. And the Testbench, this is the Testbench. All right, so the concept, the method is the same as what we have learned just now. So I will not explain here, so you can go back and try to learn on your own. All right, so I want to simulate here so that we can see the output. Oops, I should, hold on, close the previous one. This one is the previous one. Okay, so this is the traffic light one, still running. Okay, so we have, this is the output, and here is the output from the Testbench. So let's look at this. At time 20 state is this state, the first state. So of course this is for safety purpose, and we have rate L1. So this is L1 is red both in this state. Yeah, so all are red, so this is correct. And next we go to the state, this L1G on, and this one should be green. L1 should be green, L2 red, L3 red, so this is correct. And now yellow, L1 yellow, still red. All right, and because this is initialized part, this is still yellow, yellow, red, red, and then before we have on red for safety, and then before the L2 turn to green, so this one is here, L2 turn to, where is L2? L2 turn to green here, this state turn to green, and so on. So all the output are correct, and we can see actually in the here. So in the simulation here, because I still use 1 nanosecond, so we actually want to see whether it is it's produced the correct output or not. Yeah? So this clock is very fast actually, but in practice, when we use the FPGA later on, so what we need to do is we need to have the clock that is 1 Hertz, which is 1 second period, where the clock to the counter here should be 1 second. All right, 1 second period. So we can create that using the clock divider to get the 1 second period. Right, should be no problem. But for simulation purpose, we can use this 1 nanosecond to represent 1 second. Right, 1 clock cycle, sorry, 1 clock cycle to represent 1 second. Okay, so let's look at the this is the counter, so it's better to look at using unsigned view. So we can see that after we reset, so all this is the light, L1, L2, L3 red, and then this is green, right? For start at 20, 19, 18 until 0. Where is it? That, sorry, until 0. Yeah, here is 0, and we change to yellow, and this one is still red. L2 still red, L3 still red, until it's changed to red. Yeah, red, red, red. This is for safety purpose for 1 cycle, and then it's where is it? Sorry, smaller. Yeah, this is for 3 seconds until this one change to red. Change to green. L2 change to green, and this one is red. This one is red already, and green for, of course, 20 seconds before turn yellow here and turn red here, and the next L3 should go green, right? And the sequence repeated here, green again, and 3. Okay, so this is a very simple implementation that demonstrate this flow. Okay, any question before we go to your project?
No, doctor.
Okay, if not, so maybe we can use the same traffic light. Yeah, this can be UTHM entrance or any other traffic light. Yeah, now we want to create a better traffic light where it's more intelligent, we can say that, or smart traffic light, right? Where we have many sequence like this, we have many lights like this, L1 and L2, all right, this flow, we have 2 red because the flow is different actually, because here, for example, if you look at the UTHM traffic light, this will go to BP, So it's not read at the same time, right? It's read at the same time, but the green for L1 will be longer. This one go red first, yeah, because this is main road before both are red. So you have two lights here for this one only. Also, for L3, you have two lights. Sorry, this flow, you have two lights for U-turn and also for go straight here. Right, and of course L5 you have only one, yes, one only, right? So we have 5 lights now, L1, L2, L3, L5. Also, we should have, and actually if you look at the UTHM traffic light, it has a sensor to detect whether you have car waiting here or not, here or not, and also here or not. Yeah, so in normal traffic light, so normally the sensor is under the road surface. So they use what they call the loop detector, which is the inductor that detect if the metal, the car, is on moving on the detector. The detector is actually the coin, yeah, the inductor. All right, so it will change the flow of the current, yeah, when the metal moving near to the coin. All right, so it used as a sensor. Okay, so that is the most sensor that we have on the road. Another sensor is by using the camera, yeah, the infrared camera, to detect whether there is an object in front of the camera or not. So if you go to the junction Tesco, yeah, the Tesco junction now is Lotus, right? Not Tesco anymore. In Taman Yu. So the traffic light there, the sensor is using the camera instead of the loop detector. So there will be a debate whether which one is a good. Of course, the manufacturer that use the loop detector say that the camera is not good because when raining, when the view is not good at night, all right, what happened? So that is the drawback for the camera one. And for the camera manufacturer, so it will say that yes, the loop detector, the drawback is that you need to install under the road surface, so you need to break the road surface, right? So it's costly, so the maintenance is very costly. That is the problem. And again, in Malaysia condition, right, where the contractor for the road and the other the TNB, the telecom, and is not working or not synchronized, we can say that, and they not communicate. So if you put anything under the road surface, maybe tomorrow JKR or TNB will go and dig the hole there and will break your damage your sensor, who knows, right? So that is the problem with the loop sensor. Yeah, but it's a debate. Yeah. So now we are not concerning about what is the sensor that we use. So because we want to design the controller, so let's assume that the sensor, we just receive the signal from the sensor, whether the car is there or not. Yeah, for example, the sensor will produce 0 if there is no car, will produce 1 if there is a car waiting here. All right, that's it. So our input is either 0 or 1. So we assume that the sensor will provide the input for our controller. So we will not designing the sensor. We just receive the signal from the sensor. 0, no car. 1, we have car. right? So this is good if, for example, there is no car waiting here, so we can skip this sequence. So it will make your traffic light more efficient, right? Because, for example, if there is no car here, but you still turn this flow to green, so the others must wait, must stop for this flow, although there is no car here, right? So this is not efficient. But if you have the sensor, if there is no car, so you can skip this flow, and you can go to the next flow and let this flow to be always on, for example, right? That is a good thing. So we have 3 sensors to detect whether we have car here or not, we have here or not, and we have here or not. So that is the first thing what we can do. So you can use this one and modify this flow. So how to do that? Actually very not very, as you can say that, not that difficult. So we can give you example. Wait, I get the example first. Where is it? Okay, this is the example. This is yeah. Here, for example, yeah, here. So this is example. For example, if we have this is from A. So for example, from L to yellow, all right, this flow, we check whether you have the sensor is 0 or 1. So if 1, we go this flow. If 0, we go this flow. All right, so that is how we check the sensor. All right, so that is the first thing. Now let's back to this. Okay. All right, so to check is easy, not that difficult. So you can try to do that first. Now, this is what is more, more innovative. Yeah, you cannot see this in any of the traffic light that we have yet, where instead of only check whether we have car or not, so we can check also whether, for example, if there is a car here, all right, so the car can be one in the queue, 2, or many more. So why not we can check, if we can check whether the queue is long or very short queue. So if very long queue, so maybe, for example, this is very congested now, all right? So we can change the flow so that the light here, L2, will green a little bit longer, so that you can release more vehicle here. Okay, so so it is better if we can have the sensor that can determine whether the queue is long or not. All right, so it is actually can be done using the image processing. All right, but again, we will not doing or not creating or not designing the image processing part. Yeah, we just assume that we receive the output from the sensor already. So let's, for example, we have the very sophisticated sensor that can detect. This is actually another project, right? That can detect the level of congestion, for example, at S1 or S3. Let's do something like this, where S3, yeah, this is S3. So for example, if we have only 2 cars waiting here, so we call it, this is congested level 1. And if we have more car waiting here, so this is called L1. This is called L2 if the car is here, and maybe if the car here, we call L3. All right, so our sensor 00 represent or 01 represent level 1 congestion. 10 to represent level 2 congestion, and 11 to represent level 3 congestion. All right, now it's L1, so green light for this one, maybe 5 seconds only. But if the congestion is L2, maybe 10 seconds. If L3, maybe 15, 20 seconds, depend. All right. So that is I mean, more innovative way to create the traffic light controller, where the controller can determine which one is congested, so that it can manage the sequence efficiently. All right, so that one can be done also using or by modifying our algorithm here, where we can have, for example, this is S2, for example, right? We have 3 levels of congestion. Level 1, in this case, is 0, 0, yeah? 0, 0, we go to here. 0, 1, we go to here. 0, 1, 0, we go to here. E, where is E? E here, right? So of course, the ASM will be more complicated like this. I have 3 pages, all right, for this only. But it can be done, and this is good actually. So your project, I hope to have until this level, but let's do step by step. All right, where I want you to learn this first, this more the normal sequence first, and then try to add the sensor without the level of congestion yet. Yeah, just to detect whether you have the car or not here, and let's see whether you can do it or not, whether you can perform or not. And of course, we will discuss this maybe next week. Yeah, you need to learn first, and the supervisor will look at the progress and see what you can do, and what is your issue, what is the problem, and so that we can suggest and we can solve the issue together. All right. Okay, so I hope that I explained it clearly. so that you understand what you need to do. All right. So we have 4 persons. Is it 4? Right, 4. So so this is only one project. So you need to you need to work in group, and you need to discuss how to do and try to give the solution. And the first thing that you need to do is to figure out the ASM. All right, create the ASM first. This is the most important one. After you have this, the code is actually straightforward. All right, this is the algorithm. The algorithm is the design, the behavior. If the algorithm correct, so the rest should be okay. But if the algorithm is wrong, so everything will be wrong. All right, so we are at almost 1 already. So any question? I hope that you're clear on the explanation.
Yes, Doctor.
Later on, I can refer from your video.
Yeah, Irfan?
We can refer from your video if we cannot understand.
Okay, sure. Okay, I hope this is not too much for you. This is a good thing to learn, a good thing to do. All right, so that you get something from this intern, yeah. And remember, you need to present this to your industry supervisor.
Who is our industry supervisor, Doctor?
Yeah, again.
Who is our industry supervisor?
I'm not sure yet. Need to ask Dr. Nabiha. Later maybe Dr. Nabiha share.
Is it week 10?
Yeah.
Our presentation week 10?
Yes.
Okay.
Okay, so don't worry, because the example, the design is I will give to you. So you just try to understand the things and you modify from there. So normally when you go to work out there, also the design, you will not design from zero, from scratch. All right, you will have the design and you need to modify the thing, add the value and so on. Okay.
Okay.
So if no question, we will stop here. So the next meeting will be next week, Sunday, right?
Doctor, may I ask about the guidebook of the test bench?
Yeah.
Because we have roughly draft the content of the test bench lah, but we do not which format we need to follow.
Oh, okay.
So we just write the content only. May Doctor have
If you have the content, then it's good already. So you can maybe you can maybe next week, during the meeting, you can send to us first. All right. So that
by email or send in the Telegram.
Telegram also okay.
Telegram, okay.
Yeah. So that we can discuss later. I'm not sure also the about the format. I will discuss with other lecturers. So what is the I mean the format, the layout that we want. But if you have the content down already, that is good. So we just fit in the template if you have.
Okay.
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 Thank you.
Thank you.
Yeah.
That's all.
Okay. So if no question, thank you very much. See you next week. So and
Okay,
again,
thank you.
although our next meeting is next week, you still can ask anything through the Telegram. Yeah, you can discuss or if you have any issue, you can ask there. Okay.
Okay, thank you, Doctor.
Thank you, Doctor.
So I will
Alright, thank you,
share.
Doctor.
I will share the material, the code, and this ASM chart on Telegram. All right.
Okay, sure.